This is after I just encoded that video. There's something I wanted to add to the last one just before going on to this one. I still have that. I called it Do Magic Trick. I remember I was talking about hiding keys in the registry. Well, that's great and everything, in fact, and works. And what's even better about that, if I can get my magic trick to go, you see the problem with the file one, as far as I know, you know, I've got that crazy big long directory. Which I might be able to get out of that one with some renaming, because it's not that many subdirectories deep. But the problem is the functions that you would need, even if you suppose you go to the next directory, right? And then you go to the next directory. Okay, now already I can't do that, but I could, you know, maybe rename one and keep renaming and so on. But still, there's a limit. I could start out with, you know, 1,000 single-letter subdirectories first. So that means that you won't be able to browse to a directory in order to rename it. So even if you knew one directory, the function that you need to get a listing of the directory, I mean, I'm not talking about MFC or anything like that. I mean, the base function, find first this function, okay, base. This function fails on long path names. Now, I don't know if this is really the base function though. It's in win-base.h, but you see there's another set of functions from which these functions are created, from which the win-base API functions derive, and those are the NT base functions, and they all start with, I think they start with NT. They're an NTDL maybe. Oops. I think, yeah, all these ones that begin with NT, there's one. No, that's not it. Oh, maybe get first or something. Oh, come on, I just saw it there. Get, let's see if this works. Get note. Okay, OZW, those are the ones. Going to add them. Nailing to the file. Soft start profile, open file. See, like ZW create file is the function that gets called by the base API function create file, I'm pretty sure. And these ones might not fail on the long path names. But you can't use this to browse for the file at the end of that long path. You'd have to find some trick, like renaming directories, which may or may not work. One time I got caught and I couldn't rename my way back to a small enough path that I could actually press the delete key on it. And I forget how I actually got rid of it. Because it was a case where I was experimenting with the same thing, but I forgot the name of the file, right? And I forgot the path. Oh, but the path wasn't that bad because it was all repeats. It was repeating the same path, so I knew that all I needed to do was find out what that file name was, and I could eventually locate it by name. And but I couldn't remember. I'm sure that there's something for walking through a directory in this collection of functions. However, that may be the case. That may be the case, but the registry doesn't have that problem. And that's what I wanted to show you, that it doesn't have that problem. And so, really and truly, you can hide registry keys in the registry. Here's a thing, registry key, right? And there are values here, and I can enumerate those values, even though they're too long for regedit. That's the magic trick here. Let's see. It's just going. All it does here is open that registry key, and I call my enum names function, and print out the key's name and print out the key's value. That means I can walk through them. And that means that suppose that you have a program and there are some settings that you store in the registry, and you don't want people to muck around and fiddle with those settings. All you got to do is just make them whatever the name, a minimum length, so that this program cannot edit them, and then you can be sure that those registry values are safe from people mucking around with. Of interest, of course, is whether or not such values already exist. Okay, now you don't see much. Maybe I'll put a sketch here. The names started out, they were quite long when I shortened them. They were randomly generated. And they were so long I made some shorter ones. And it doesn't matter because I can walk through them. Of course, you could delete the key itself. So the 0th key value is the secret key 1, and here's its name. Okay, that's in here. And here's the next one, secret key 2, that's its name. And there's a whole bunch of them, big long ones. Eventually, I started making them smaller. Because I was curious if I was getting, made a function that puts in th or rd or whatever. And I don't know, I just wanted to see it, I guess, easier. Now, clearly the limit is not very big, right? This is a full page of this is 2,000 characters, so that's, what is that? That's what, 1, 2, 3, 4, 5, 6 lines and a bit of 80. So that's 400 and something. Probably 206 max path, right? It's going to be max path. I guarantee you. If I make a key in there, you try it yourself. I guarantee you it's going to be max path. If you make it a key, max path characters, you'll see it. Add one more character and you won't see it. I bet my life on it. You know what the code looks like, right? Car or T car, TC, the value name, the key name, the value name, you know, underscore max path bracket, and then get, which of course fails. And so this program can't display it, and you just saw that I'm displaying them, and so therefore this program can display it. It's simply a bug. And if you wanted to, you could take advantage of that bug and just add like a 260 letter A's in front of all of your values, and then put your value name after that, and they'll all be hidden. And if you wanted to spoof people, you could put copies of the values that look legitimate, you know, even synchronize them. You could synchronize the shortened versions of your key names with the longer ones that nobody can see, so that if you make a change, you can see. If your program makes a change, you can see if that's correctly reflected in the registry, right? But you wouldn't be able to use the registry to modify those keys. Those would be program write only keys. If you wanted such a feature, it's available. Okay. Hello there. Again, this is Al. Just wanted to give you a little heads up on what I've been looking at. In fact, looking at XML and trying to parse those XML files. Now, the lib works perfectly, but what I had previously was definitely wrong, and so I have to do this all over from scratch. And I'm trying to build a structure, as you can see, what I'm looking at, for organizing the information in a XML file programmatically in a way so that it's easily accessible. What I hadn't realized in my other code, which I can't really show you in this tiny little window. Well, I can show you in Notepad or something. In my other code, which is in here somewhere, here, which was like 3 lines long. This isn't actually what I have, isn't that much. It looks like a lot, but that's just the data. What I was making extensive use of was this function called find data. And that would take, just like the registry has keys, it would take a key value, which is essentially the path, something like this on the bottom here, right? And it could return the data. There's also attribute information and some other information as well that I wanted to add. But if you look at this code, the way this code works is I have just a linked list of structures called data, right? And I go through the list, and if I don't find one with the same key value. This is using double equals. I don't know about case sensitive. Oh, I converted everything to uppercase, but I'm not doing that this time around. If I don't find it in the list, then I create a new one, I add it to the list, and then call this function again, because this thing has to return a reference to something in this list. So I can't return this object. This is a temporary. Now the problem is that unlike the registry, and unlike the file system, and unlike everything else, not only are the path names not an identifier for the particular section or object within the file, but in the case of XML, the path name itself is completely useless, because you can have two things that have exactly the same path name and they would refer to two different sections. That is, it would be like c.alan.bat. Okay, now you could have two of these. In an XML file, you can have two of these. What's different, and the full path. I don't mean, like one is in a different section. They could be in the same section, have the same path. And the reason is, becomes clear when you just take a look at one of these XML files. Is that where I put it? I probably got, no, I don't have it open actually. It should, no, I do have it open, but I can still view it. Where is it? Say it was called, let me see here. It says services. Here. No, not there. Well, yeah, here. This counts. Okay, this stuff is called attributes. This stuff, or this part, is the name of this particular node. If it's a tree. Here's a node, and it's a node called snap-in, right? And in snap-in cache, there are 5 snap-ins. See? Now these aren't the data. You can have in between something's open and closed. Here's the close. Now, I don't know if that makes a difference. These ones don't have closes, do they? Maybe this should be considered data. Well, it shouldn't matter anyway. Here's an example of data. So you say binary, this is some attribute. Here's a bunch of data. And eventually there should be a slash binary. Here, see? Now here's another one called binary. And here's with a different name. But that's again an attribute, some data, and a close. Now here's another binary. It doesn't have any attributes. You see? So if you were to try to specify any one of these, you would use the same path. Right? In terms of XML, it's binary storage, which is a sub underneath console file. It seems to be second level. Yeah. So you'd say console file / binary storage / binary. Well, that's no good, right? You could include, I suppose, this attribute, but there's no requirement that the attributes have to differ. Let's see if we can find an example. The attributes could be the same. I'm sure that this would be fine if I just repeated this 5 times. It's still a valid XML file. I just have 2 or 3 copies of this snap-in, I could change the data part, right? And I'm sure that we would find, here we go. Those are different. Essentially, what I'm saying is that the path name is a dumb way to try and search for the data or the attributes associated with a particular node. Well, so here I'm trying to build a structure based on the idea of we're going to draw a picture, the worst possible. Maybe paint. Help. If I draw a nice picture, I could use it as the icon. I would like to draw a line. No, first I want a circle to represent the root. Okay, good enough. Now the root is kind of empty, but it has one child. It always has one child. Let's go to this size, different color. How about squares, not circles? The root's special. Where'd it go? It's there. Alright. Okay, square. So now here's a node. We'll call it node 0. This is really the root. I made a thing called root, and I'll probably change it to this to make this the root. All this thing contains is one pointer to the only child, which is really the root node. Okay, now line again. So now a node, if you remember just from a second ago, can have subnodes. Other things that start with angle brackets. All immediately below itself. So now the way I decided to code it is, well, should I go this way or that way? We'll try going this way. Let's suppose, on green again. Let's suppose that this node has 5 subnodes. One, 2, 3. We don't have to start from there. 4, 5. So that's 5 boxes. Not green. And they could have the same name, and often they do. Now I'm calling these children. So these are the child nodes of node 0. Okay. and there are 5 of them. Each of these can also have its own children, and then I've decided to simplify my life that in only one direction the children can have siblings. So now I'd like a line with this kind of thing, but maybe smaller. I can do that. So this here, this is the sibling of one. Well, if I numbered them, in red, black. 1, 2, 3, 4, 5. So I would say now 2 is one's sibling, and I've called it first sibling, but really I should just call it sibling because I'm only making there's a first child, okay, and then all of its siblings. So if you manage to locate the third sibling, you couldn't get here. The way to get here would be to go to the parent and then go to the first child. So you can always get everywhere, but in order to not have to maintain another pointer, I only have a one-directional sibling chain. So these are siblings. Make that clearer by doing this. And making this thicker. So all of these things are siblings of 1 and represented by an arrow. And then now each of these can have their own children, and those children can have siblings. And I'm also maintaining the parent. So in each of these, there's a parent. I want to have a parent. Purple. Text. Black text. Mark. This is equal to the parent relationship. So these lines indicate that node 0 is 5's parent, and 4 is 3 and 2 and 1. And 0, there's also another purple line here. Oops. I should have arrows, but whatever. Okay, so now that, so a node involves a first child, a first sibling. Now, node 0 might have a sibling. It's possible. Red. That would be, I guess, 6. I don't know what we call this, but I don't want to go backwards and forwards in numbers, so we'll call this node 6. There's an implicit node 1, 2, 3, 4, 5. So this is the sibling. Node 6 is a sibling of node 1, and so therefore it's also true that node 0 and node 6 have the same parent, this root here. Again, children, and so on and so forth. So there's a child, there are children, and the children can have siblings, and the children can have children, and everybody's got a parent, and it's all a great big happy family. Text. Big text. Let's set this. Oops. Text. Great big happy family. Here it's the wrong color. How about red? No. Here. No, I don't like that. Here. I know this looks like I've selected blue. Blue. Text tool. Oh, let's see. When I pasted it, it remembered the color. That's not a good feature. That's one of the things that's bothered me since day one, especially to do with rich text format and things like that, or Word documents, or copying something from a web page into something that supports rich text, and all you want is the text, but instead it comes back, formatted. So you got to open Notepad or some other text editor that has no formatting, paste it anyway. So this here, Great Big Happy Family, is what I'm trying to make. And I'm pretty happy with my picture. So how to do that? Let me place this for long. I have a quick way to get to here by having pictures. Icon for the directory. And as you can see, it's sort of looks right. Here's the root node, which has its single. At first, I have the nodes on top, but I want to see the data in an easier way, so I put the path first in the struct, which is not usual. The path meaning internal. The other one's gone, but the path, like a file path type thing with backslashes. So the root node doesn't really have any path, and none of its members are valid except for its child. It's one and only child. It can't have any siblings, or else it wouldn't really be much of a root now, would it be? Okay, now so the first child, which is really the root node of all this, is called NMC console file. and the attributes for that node, okay, this node is actually going to contain everything. Are this console version, program mode, something something, and now this is the string version of the attributes. It's really stored as an array, but I can't seem to make this display nicely, so what can you do? Because this is a template thing. Now, it has a child, it has a first child. Okay, console file ID, no attributes. Now the parent, that parent will be, as you can see, it's just back to the parent. It has this one has a sibling called frame state. So we got console child and frame state are siblings because they're the same level in the tree. And this one happens to have some attributes. And this sibling also has a sibling called views with no attributes. And this one has a child called views view, which has attributes. And it also has a child and no sibling. At this point, you know, I've only pressed F5 about 30 times with this breakpoint to watch it build up slowly. So under views view, there's a child called bookmark with these attributes. I'm not gathering the data currently. That's easy to do. But it would be a mess to have everything together. Now this one, bookmark, has a sibling, and this is where I would have got messed up before, because its sibling's path is exactly the same as itself, but it has different, even if it has the same, no, it's got a different name. This one's called a selected node, and this one's called a root node for bookmark. Okay, now as you can see, views view window placement is a sibling of bookmark. Right, it's the same level in the tree. And then view options again is another sibling. Okay, and now there's no more siblings and no more children at this point. Now this child here is a child of window placement, and we didn't get to there, do we? You can see though that it's all organized correctly, and we got the children, and the parents should all be correct. There should always be one back, and with the correct pointer. So here I'm looking at the parent of window placement point, which is window placement, right? And the value 18cc2a8 should be window placement. There's window placement here. That's this object. Where is it? Here. No, it's sibling. Window placement. First sibling. Child. No, I can't find window placement. Oh, it's this thing. It's this thing. 18cc2a8, right? What was the parent I was looking at? 18cc2a8. So it's correct in terms of not just the path name, but the pointer. And so two different things with the same name now have their own special node. And so I'm correctly deciphering that. And I mean, the code is not that complicated. It's just that it's hard to look at that output. But well, that's my cleanup. I started writing this function first because I thought that if I knew how to clean it up, I'll know how to make it. And it took me a couple runs, but this XML library, as you go along, when a new node begins from wherever you are, this function gets called back on. And I'm using this pointer of an object of this type as my reference. So I cast that. So whenever it says start, that means it's a totally new thing. So I create a new node. This here just sets the attributes taken out of this, which is a pointer to pointer strings. So there should be an even number. It's A equals B. A equals B, A equals B, repeated, and ending with a null. I guessed that, and it happens to be right. It's just hacky, being a hack. I'm maintaining something called current path in the tree. Current path in the tree, as we're going up and down. If that's empty, that means we're nowhere, we just started out. Then this new node I'm creating, I'm setting equal to the child of the root. Okay, and that should only occur once. Now I'm actually taking the element name, which is in cars, not T cars, so I've got to use my special cast. I'll deal with this. I think he's got Unicode support. I put a slash in front, and then I add the new node's name. So the current path has gone up one level, and the new node's path is equal to that path I just set. Now there's something called myRoot, which is an optional thing. You can specify, if you trust and believe that specification is guaranteed to be unique, you can specify a path name to act as the root from which you want to extract data from, so it won't start adding things until it hits your special thing. And this is not totally correct, in fact, because oh, wait a minute, is that the same myRoot? Yeah, myRoot path is something you set. It's an option. I might even throw this away completely, because once you got the whole thing, then you can fiddle around. It doesn't take long to parse the whole file. Now, once you've created a new node, and if you believe that this pointer is maintaining a current node as the current root, right? Then it shall be true that the new node's parent is equal to the current root, whatever it was, and it's going to change. About to be overwritten. And then now here's the entirety of the code after that one step. This step you can ignore, I'll probably get rid of it. If the current root doesn't have any children, right? Then we're any first child, sorry, which is the same thing, I guess. Then we're going to set its first child equal to this new node. Now the reason why you wouldn't just do that immediately is because the current root might already have a first child and we're adding a sibling. So in the case where there's no first child, we add it. But if there is a first child, right, and if that first child is not equal to the new node, if this seems to be tautologically true, there's no possibility that could not be true, unless I set it up here. Oh, I could, yeah, in the root case, the root's first child gets set equal to that. So there's one case where this could fail in the root case, so we would skip this for the root. Otherwise, in the normal case, the first child would be either null or something else, right? Well, it's not null because we checked and we've done that case, so it's something else. Now I want to walk through the children of the child, right? So I've called this sibling. So I take the first child of the current root, right, which we haven't modified yet. We're moving to the next level, but current root is still one level behind. Its first child, I'm calling sibling. And I'm trying to locate the last sibling starting from the first child, just like a regular, it's just a linked list. While this is not null, right? And I know this is not null because I've just tested right here to ensure it's not null. Save off the current one and then take the sibling, keep going until we hit null, and then the last sibling's sibling will be set equal to the new node. And now finally I set the current root equal to our new node, and that's the entirety of the code. As for when we reach the end of a node, this gets called by the library, and it appears to be doing it correctly, even in those funny cases that have, there was a funny case, and I haven't really tested it, but those ones that didn't have a closing brace, like this, point, that's its closing brace. There's no slash point. So I don't know how, we'll see. Well, we saw them in there, didn't we? We'll try it again. Use view. We don't have to go very far. All we got to do in this case, right, when the element ends, is set our current root, set the new root equal to the current root's parent, and then cut off one thing from the path. I'm going to run this, I don't know how many times, but I want to see that. Oh dear. We need to have a breakpoint. I don't know how many I need to get that list of points. Child, console version of the child, console ID has sibling, main state which has child, which has window placement, and where is that thing? What are we looking for? it's going to be under frame state. No, it's going to be under views. So that's not going to be it. Views. Okay, views. Have a child called view. Not hand. Okay, views view, and then window placement. Views view, window placement, sibling or child. Child. Bookmark. Okay, well there you go. Bookmark doesn't have a slash bookmark, right? And it gave me a start and an end. It should have given me an end for that. There's a sibling, also called bookmark. So it correctly bracketed these two bookmark elements. So it's working perfectly. And now I've got a great big struct. And it contains all of the data. And if I want to look something up, it's just a matter of figuring out an easy way to walk through this structure. And I don't think that's going to be very hard. Okay, so that's that. The XML thing works great. And I've got a class that's nearly finished for implementing the parse and then looking up bits of data, including the attributes, the data part, and it's all in a nice tree-like structure. Okay, so I'll let you know. See you.